Let's talk about surface integrals. So on the very first day of class, we offered a motivation for the entire course. And one of the slides we went over was this slide. But at the time, we didn't have enough calculus at our disposal to actually develop this concept thoroughly, but we do now. So the context for this first part of the video, or the lecture, I guess, is let's say that we have a sheet of material that conforms to the shape of a surface, maybe called S, in 3 dimensions. So here what we're looking at is some sheet of material, and let's say that the idea is that we have a scalar field on 3 variables that measures the density in kilograms per meter squared at every point on the surface. So let's say, for example, that we chose one point P1 on the surface and plugged in the coordinates for P1, and the scalar field spit out, say, the density 7 kilograms per meter squared. Maybe if we plug in a second point into the scalar field, we get another measurement, 17 kilograms per meter squared. Maybe at another point, the density is 3 kilograms per meter squared, and at another point, the density is 21 kilograms per meter squared. So the purpose of this little f is to measure density at every point on this surface. And here we have like 4 samples. So the object that we're about to define is called the scalar surface integral of our scalar field over the surface. And before we offer the precise mathematical definition, I want to state up front what its purpose is. The purpose of this scalar surface integral is to calculate the mass of the surface. And in this context, if density is in kilograms per meter squared, the mass would be in kilograms. So the notation that refers to this is 2 integrals, subscript surface, and then we integrate f d capital S. Okay, so let's give the mathematical definition in this situation. So when we work with surfaces in vector calculus, we start by parametrizing the surface just like we did in the previous lecture. So let's say that we have a parametrization, bold x, which is defined over some 2-dimensional domain of a surface. The scalar surface integral of a function little f along the parametrization is defined notationally as 2 integrals with a subscript bold x of little f d capital S. And this is defined as the ordinary double integral throughout the domain of the parametrization of f applied to the parametrization multiplied by the norm or the length of the standard normal vector for the parametrization. So to take a scalar surface integral of a scalar field, we take a double integral over the domain of the parametrization of f applied to the parametrization multiplied by the length of the standard normal vector for the parametrization, dA. And here, what we're doing is we're adopting new notation. When we write d capital S, this is meant to stand in place for the length of the standard normal vector, dA. So here, ds is appearing in the notation on the left, and then on the right, we're looking at the length of the standard normal vector, dA. Now, if we track the units in this definition, we get an interpretation of our definition of scalar surface integrals. So remember, the standard normal vector is defined as the cross product of the 2 tangent vectors. So let's look at the units here. Well, the units for little f should be mass units per area unit in the surface S. If we look at our 2 tangent vectors, when we cross them together, we end up with, and take the length, we end up with a scalar quantity whose units are area units in S per area unit in D, And then dA in this context is meant to measure area throughout the domain, so that this would carry the area in D unit. And when we multiply these quantities together, the idea is that the area units all cancel out, and what we're left with is mass units. So our double integral actually does calculate the mass of the surface. So let's look at an example. Here, we're defining a surface S to be the first octant part of the plane defined by the equation 4x plus 2y plus z equals 12. So here we have a visual representation of this particular surface. We're only looking at the part of this plane where all of the variables are positive, and one way to visualize this in this situation is to figure out where the plane crosses the coordinate axes. When y and z are equal to 0 here, we're looking at the equation 4x equals 12, which is solved by x equals 3. When x and z are 0 in the equation for the plane, we're looking at the equation 2y equals 12, which is solved by y equals 6. And when x and y are equal to 0 in the equation for the plane, we're left with z equals 12, which is where the plane crosses the z-axis. So we have this nice triangular-shaped region in space. So let's say that we wanted to do a scalar surface integral. An important ingredient here is a parametrization of the surface. So how might we parametrize this surface? Well, one way to do it is to note that this surface is living above a two-dimensional domain in the xy plane. This two-dimensional domain is another triangle where the vertices are the origin, and then x equals 3 and y equals 6. So the idea is that if we zero out z here, we're looking at the equation 4x plus 2y equals 12, which is a line with intercepts 0, 6, and 3, 0. So the line itself is described by the equation y equals 6 minus 2x, which is obtained by zeroing out z here and then solving for y. So how can we parametrize this surface? Well, let's parametrize with bold x. And the idea is that in this equation, we can solve for z. So let's let x and y vary in the domain in the xy plane. And then let's force z to satisfy the equation for the plane by setting z equal to 12 minus 4x minus 2y. So in our parametrization here, what we're doing is we're forcing the third coordinate to play nicely with the previous two coordinates so that all three coordinates together satisfy the equation for the plane. Once we have our parametrization, we can calculate our tangent vectors. We're parametrizing with variables x and y. So the first tangent vector would be bold t sub little x. And what we're doing here is we're just differentiating each one of the coordinates with respect to x. So in this case, we should get 1, 0, negative 4. And then for the second tangent vector, we're differentiating every coordinate with respect to y. When we differentiate here, we should get 0, 1, negative 2. Now, to calculate the standard normal vector, we take the cross product of our two tangent vectors. And when we take the cross product of 1, 0, negative 4 with 0, 1, negative 2, we produce the vector 4, 2, 1. Okay, so now we've successfully parametrized this particular surface, and we've calculated the standard normal vector for this parametrization. When we go to calculate any scalar surface integral, however, what the ingredient that will matter is the length of this standard normal vector. And for this particular standard normal vector, all of the entries are constants, so the length is equal to the square root of the sum of the squares of the coordinates. In this case, we'll get 16 plus 4 plus 1, which is 21. So the length of the standard normal vector here is just the constant root 21. Okay, so now let's say that we have a density function. Let's suppose that density throughout the surface is given by f of xyz equals x times z, and the units here would be kilograms per meters squared. Well, how do we calculate the mass in this scenario? Well, by definition, the mass is equal to the scalar surface integral, where here we're taking the double integral over the parameterization bold X of f d capital S. And to calculate this scalar surface integral, what we're supposed to do is take a double integral throughout the domain of the parameterization, which is this triangle in the xy plane. And then we need to apply the scalar field to the parameterization. In our parameterization, x is simply equal to x, y remains equal to y, but z is replaced with 12 minus 4x minus 2y. So the scalar field here, or the density function, is x times z, but now we're keeping our x and then replacing z with 12 minus 4x minus 2y. We then need to multiply by the length of the standard normal vector, which we previously calculated as root 21. And then over this domain, I'm choosing to integrate dy dx by using vertical slicing. So the bounds for y in this case would range from 0 up to 6 minus 2x, and the bounds for x range from 0 to 3. Now we're left with an ordinary double integral that we can integrate dy dx, and when I did the calculus, I ended up with 27 times root 21, and the units after taking this scalar surface integral are kilograms, because the density was measured in kilograms per meter squared. Let's do another example. So here, let's let S be the cone with height 1 and radius 1. So a visual representation of our cone looks like this. We have a cone opening up about the z-axis, where here the height is 1 and the radius is 1. Well, how can we parameterize this surface? One way to do it is to invoke the idea of cylindrical coordinates. So we can describe this cone in cylindrical coordinates using the variables r and theta. And so what we're doing is we're keeping x equals cosine theta. We're keeping y equals sine theta. But now we want to enforce the equation of the cone. And the equation of the cone should be z squared equals x squared plus y squared. To ensure that z squared equals x squared plus y squared, we need to set z equal to r, because in cylindrical coordinates, x squared plus y squared is r squared. Once we have our parameterization for the cone, we can calculate the two tangent vectors. We are parameterizing with the variables r and theta. So our first tangent vector would be t sub r, which is obtained by differentiating each one of the coordinates of the parameterization with respect to little r. In this case, we get cosine theta, sine theta 1. And then for our second tangent vector, we're differentiating with respect to theta. Here, the coordinates end up equaling negative r sine theta, r times cosine theta, and 0. Now, we use these two tangent vectors to construct the standard normal vector. The standard normal vector is the cross product of our two tangent vectors. And when we do the cross product here, we end up with coordinates negative r cosine theta, negative r sine theta, r. And remember, when we're doing a scalar surface integral, we always end up multiplying by the length of the standard normal vector. So in this case, we want to calculate the length of our standard normal. In this case, we're summing the squares of the coordinates and taking a square root. Well, here this ends up simplifying to the square root of 2 multiplied by r. Okay, so now we've successfully parameterized our surface and calculated the length of the standard normal vector of our parameterization. Let's suppose now that we have a density function. Let's say that temperature throughout the surface is measured by the function f equals 5 times x squared times z, and let's say the units here are degrees Celsius per meter squared. Well, how would we measure the aggregate temperature in this region? Well, we do so with a scalar surface integral. Let's now take the double integral throughout the parameterization of little f ds. According to our formula, we should take a double integral throughout the domain of the parameterization. We then take our function and replace the x's, y's, and z's with r cosine theta, r sine theta, and z equals r. And then we multiply by the length of the standard normal vector, which is the square root of 2 times r. So now we're taking a double integral where the integrand is f applied to the parameterization. So now we're looking at 5 times x squared times z, where x is replaced with r times cosine theta, and z is set equal to r. Then we multiply by the length of the standard normal vector, which we just calculated to be the square root of 2 times r. And now this parameterization is defined for r's ranging between 0 and 1, and theta's ranging from 0 to 2 pi. So now we have an ordinary double integral to calculate, and when we do the calculus, we end up with the square root of 2 times pi, and the units here should be degrees Celsius, because the density was degrees Celsius per meter squared.